Okay, so let me just revise once what all we have studied. I mean, I'm just gonna go through the main results and the stuff that we have used. So I'm not gonna go through the process. Yeah. So we started off with using the Chapman-Kolmogorov for the discrete case, which had this thing. So it was called Markov chain. But now what we call it is Markov jump because we're making jumps in instantaneous time period, which we denote as small h. And we looked at our example of healthy date, and we saw that the matrix wherein we have the rates everywhere in its elements is called a generator matrix. And let's say if you have the probabilities, it is just called the transition matrix. And then we had a look at how do we make certain assumption of there not being any more than one possible jump in a particular short span of time. So either the state will be same or the state will be the immediate state. There can't be two jumps or two steps ahead. So I guess this is what you have. And then this is how you define the probabilities. Again, this is the probability that you start off at I and you end up at J in H time interval. This is just H, which is the time period multiplied by the instantaneous rate of the transition plus OH. This in limit goes to 0. So that is just to account for the other cases that have a very negligible chance of occurring. And then we also saw the relationship between mu I and mu ij, and we know that the addition of a row in a generated matrix is supposed to be 0 for it to be a well-defined one. Okay, then we saw that to figure out probabilities, if we are given the transition rates, there are two possible ways. So one is we see that we jump at the last, and the other case was that we jump in the first. So if you substitute this in here in the Chapman-Kolmogorov equation, you basically arrive at something like this. And this is known as Kolmogorov's forward differential equation. And something else if you do, which is if you jump first and then you span over the t time period, then you will get something like this, which I haven't quite derived, but I guess it's similar. So this is the end result in matrix terms. And in the previous lecture, I guess we just saw the differential equations, backward differential equations for the Poisson process and the Heldesic model. And then this is something important that we studied. So we studied something about the holding time, the waiting time, the occupancy probability. And as we have already, I guess it was the very first lecture, I guess first or second lecture where we derived that the inter-arrival times between the Poisson process is exponentially distributed. So I guess I haven't derived it here again, but you can see that it has e raised to minus lambda it. So again, this is such because we're looking at P0 being greater than some P. So I guess that's cool. And then we kind of came to conclusion that lambda I, which is the total force of transition from state I, total force of transition from state I, or you can also say out of state I guess it's the same. Okay, from state I can again be a bit so when I write from state I, it could mean that it goes from I and it again lands up in the I. So I think it should just be out of state I. So when I'm saying out of state I, it means that I cannot return back to I. And that is what this lambda I here is. So the expected time that you think you might wait in a particular state is 1 upon the total force of transition out of that one particular state, which is represented by I over here. And then we saw, I guess this was the whole derivation, but again, this is quite intuitive, right? For us to determine this probability, if we are given the transition rate and the waiting time, this is what will be the probability that you start off from I in 0 and then you land up at J by T0. So I hope that's clear. And we did a bit of a derivation and then we solved one sum. Okay, so this was important as well, right? When I put a bar here, so if I'm writing PIIT, With a bar, it means that I stay in I for the T time period. But if I do not put a bar, if it is just PIIT, then it means that in the time interval T, the process can go from I to J and then come back to I. So what matters is that it starts in I and it ends in I. It doesn't matter where or it goes in between. But if I put a bar, then the process has to stay in I for the time period that I have specified. And if that is the case, you can see that this is the derived probability for the occupancy probability, which is the formal name. Okay. And then this was the expected time that you take to go from one particular state to another state. And this is simply, the time that you expect to be in the same state plus the time that you expect to transition out of the other states. And when you go to the other states, you have just made the formula recursive by writing mj. So again, you say that if your k is the destination state, then this j cannot be equal to k. So basically, do not go. Let's say if you want to go from h to d, h to c, why have I written c? It should be d, right? I guess, no, I guess it was Corona. Yeah. I took a Corona example, and that is why you could go back to H as well. Yeah, so then you can basically transition. So if you want to look at from H to C, you can go from H to S and then S to C, or H to H and then H to C, and so on and so forth. But again, here H to H is not permitted, right? Because this J cannot be equal to I or K. I is where you start from, and K is where you end up at. And we again had a look at one of the examples wherein we used that formula and everything else that we started. So I guess today what I want to do is again continuing with the same previous question, I would say. So uh, maybe you should just want to take a screenshot or something of the transition diagram here. And the question today that I will be asking is something else apart from these three. So let me ask another question now related to the same thing. So what I want to figure out is the probability that if a life is in sick state today, then that life will die without ever recovering to the healthy state. So that is the probability that I am concerned with. So I can write that, life is in sick state and it dies without ever going to H. So this is the probability that I want to figure out. But again, now if you, so okay, I want to just open this question to you all, and what do you guys think I should do to figure out that particular probability here? What is the very first thing that comes to your mind? So this is the probability that I want to calculate. Anyone? Again, what kind of a formula have we studied which might help us to derive that particular probability? Are you guys there?
Hello.
Yes.
Ma'am, what is the difference between the second case and the case that you introduced?
Oh, okay. I think, can you read, Vanshita, what am I asking you in the second question? Can you read it aloud?
I missed the question, like I was not able to note it down. So can you please?
Ah, okay, okay. This is the question. Read it again. So in this question, we aren't allowed to ever go to a healthy state and then die.
Yeah, but in the second question also, it states that a sick life goes into state D when it leaves the sick state. So whenever it
Wait,
will leave the sick state, it will go to D only, right?
not necessarily, right? So it's like, I mean, once you're at sick state, you can go to healthy or be dead or become terminally ill as well.
But in the second, it is mentioned that when you leave S, it will go to D.
Oh, okay, okay. So here, what we are concerning ourselves with, we have already given that, whenever you leave us, you want to go to D. Here, you can't even go to terminally ill and then go to D. But here, in this particular case, they haven't specified anything. So you can basically be dead by becoming terminally ill as well. So this is not the only part. This is the second part that you'll have to consider now. Because the only criteria there is that it should not go to the healthy state.
Okay.
Does this make some sense?
Yes.
So what do you think I can do here? I guess the answer should be pretty clear now that Vanshit has already asked this question.
So would it be like the addition of the two parts, the probability
Yeah, right. It seems like that
upon
should be the case.
upon the total?
Yeah, right. So if, I mean, that is what it is. So let's say, I mean, what you have is the mu of going from sick to dead directly plus the other step that you can take. So mu from S to T and then T to D, right? So that would be what? But again, what do you need to mention is only S to T because once you are at T, there's no way you can ever go back to the healthy state, and that is all we want to ensure, right? So that is enough. And because the denominator is going to be same, which is lambda s, everywhere you can just write it as this. So now who will tell me what are the numbers that we have here? I guess it's nothing new. So mm, yeah, 0.05 plus 0.15. So this is going to be 0.05 plus 0.15 and everything upon 1.2. And that will be your answer.
So,
So
ma'am, are we
there,
considering only the movements in only one time step?
yes. But
So
again, you
that's why
see,
only
so
POST.
yeah, again, I mean, that's why only music. So again, see, you can also consider in one time step, but again, if you look at it carefully, what you can say is in one time step, it's not possible for you to go from S to T and then T to D, right? The only condition there is that a life in S should die. There's no time boundation here. There's no boundary on the time that you're looking at. But all we know is, I mean, all we care about is that the life should never go to H, right? So once we know for the fact that S goes to T, then we know that there's no way it can go to H, and it's for sure going to die or just stay terminally ill. So all we care about is just this. Otherwise, I think so. If you want to go through the actual probability, I think so. It kind of involves all the geometric sums. So, I mean, so for someone who wouldn't have studied these Markov chains, and if you give them this graph and tell them to figure out the same probability, what they might do is, so what we do is we add all the possible sample paths, right? So the first path would be from S to D. So you have 0.05 plus S to S and then S to D. Then S to S to S and then S to D. So all of these geometric, and then S to T and then T to D. Then S to S and then S, and all those paths basically. But due to this one simple result and the assumptions that we make, this makes our life much, much easier. And this is all you have to do to figure
So
out this
basically, they've
probability.
just said that we should die in the end, so there's no time bound. So that is why we won't consider that, only in 2 time steps. It's just going to be by itself, right?
Yeah. See, the only thing that they are asking us is that the life dies without ever going back to the healthy state. And this covers it all, right? Because if you go to terminal ill, there's no way you can ever go to H. So this condition is already satisfied.
Yeah, got.
What about others? So again, sometimes actually what happens is whenever we are looking at a jump process, so we actually raised up really good questions in the class about this particular question, and these are all valid questions. Why? Because time that we are looking at is of importance as well. So whenever we talk about a jump chain, we say that we are looking at particular a very finite time interval. But if we're looking at the jump process, we say that the jump happens instantaneously, okay, in a very, very short span of time. And that is why you have these two different kind of analysis that you can do if you are looking at a jump chain and if you're looking at a jump process. And the only difference lies in between these two is whenever you are at an absorbing state, which is the D state here. So what happens in a process is that once you reach that D, the process ends, right? There are no further transitions from D. But if you're analyzing this as a jump chain, you can still go from D to D, from D to D. Basically, you behave as if you are still going in different times to the same particular state. And what helps us is to just assume that in the case of Markov jump processes as well. So this is like a very technical, I would say this is like a very technical point. And I think that is, I mean, it doesn't quite matter, but it just makes our calculations easier, I would say. So again, if you have a particular jump process and if it satisfies Markov property, then you can easily say, that the transitions happen. And basically if you examine a particular process at the time when a transition takes place, so then you can capture all of those times and basically say that this now is a Markov chain. So I guess that was just a bit technical stuff. But now let us try to solve a very good question, I would say. So what I am going to do is, okay, so what I am going to do is I'm going to draw something and there will be some questions and we'll try to answer those questions to check how much of what we have studied up until now we have understood. So you will, okay, so again in this particular model, you are not given the transition rates as well, but we'll see what is given to us. So again, this is about claims. So if we're talking about claims, there is one particular state A when the claims arrive in the claims department. Okay. And then the claims are lodged. So once the claims are lodged, they can go to either state L, and if they go to state L, it means that the investigation will be done by a loss adjuster. Otherwise, they could go in where you need more information, and then again, it could either go to LI or it could go to S, where it is already kind of settled and there's no further information that is required for this particular claim that is arrived. And once a claim is settled, it is, we say that basically the process is completed. So the process is completed. That is when when the settlement has already taken place. So I would say these are the states that we have. Let me just write here example. So these are the states that we have. So again, claims arrive. It could go to L, I, S, or to C. And once you are at L, you can go to I, or you can go to S directly, right? So if you have already lodged a claim and the investigation is being done, then in the investigation, there might be a case where you need some more information, or if there is no further information required, then it will be classified as a settled claim. Okay, so now some more information is given to us, and it says that if a claim has arrived in state A, it takes on an average 2 days for the claim before it is lodged and classified as LI or S. And once it is in the state L, it takes almost 10 days for it to be classified as either I or S. And now again, I forgot to make an arrow. Yeah. And now if you are in the state I, it takes on an average 5 days. So this thing takes 5 days, and once it is settled, it will take 2 days. So to settle down, it takes 2 days, and then only the whole process is claimed as completed. Okay, so this is the times that we expect to remain in the state where we are. So these are all those times. And C, I mean, you will stay here forever, right? Because once it's completed, the process is completed. And the other information that we have is of how much percent of A we expect will go to L, will go to I, and will go to S. So we expect 30% of the cases to require, wait, let me just check. Okay, all right. So they are saying that 1 in 10, so this is just going to be 0.1, and this is 0.5, and this is 0.4. So these are the probabilities with which your claims will go from A to either L or I or S. And from L to I, it's 0.3, and from L to S, it's 0.7. And I guess from I to S, that's always going to happen, and S to C is always going to happen. So there's no need of probability, right? Because that is the only thing that can happen apart from it being in the I or being in the S itself. So this is the model that we have. And now the very first thing that we want to do is write down the generator matrix of this model. So how do you guys think I can write the generator matrix of this model? Maybe we'll just write it here. So now what do you guys think will be your first step? Okay, so can you tell me what all information do we have? Can someone explain me what does this 2 days, 10 days, 5 days and 2 days represent? I know I've already just explained this, but I want to hear it from you guys.
waiting time.
Waiting time, right? Yeah, and what are the numbers that we have?
The probability.
The probabilities, right? Thank you very much, Manshita. Okay, so we aren't given the rates, but we only know the probabilities and we know the waiting times. So maybe the very first thing that we can do is write the probability matrix, let the probability transition matrix, right? So maybe if I just denote it as P, I can write my P. So it helps for me if I write this here, ALISC. And here I'm looking at ALISC. So from A to A, what should I write here? What is the probability that I'll go from A to A?
0.
0.
0, right? And what is the probability that I'll go from A to L? 0.1, right? So this is 0.1, A to I is 0.5, this is 0.4, and this is 0. Okay, now we go to L. L to A is 0, L to L is 0, L to I is 0.3, and L to S is 0.7, and this is again 0. And now if you're at I know there's only chance that you'll go to S. Rest everything is just 0. And if you're at S, you only go to C. Okay, so now this is your transition probability matrix. But now we want to figure out the generator matrix. So we don't know the rates. We only know the probabilities and we only know the waiting time. So is there any formula that we have studied which includes probabilities, waiting time, and the rates, so that we can exploit that particular relationship to figure out the rates that we have? Go through your notes and see if we have something of that nature. Anyone? Maybe you can also have a look at the summary, which is at the end of the chapter. Over there, you can see all the major formulas in a page or something.
Can we use in the summary the probability that process goes into state J when it leaves state I?
Exactly, yeah. Absolutely correct, Vanshita, right? So what does that formula say? It says the probability that the process goes into a particular state J when it leaves the state I is what? Is mu ij upon lambda I, right? So let me just write it here. Some probability you go from I to J is mu ij upon lambda I, right? So here we know Pij's, which are all of these, right? And we know lambda I. But what is lambda I? Let's just figure out lambda I for each of these. So let's do that. What is lambda A? Anyone? What is lambda L? What is lambda I? lambda S, and lambda C. What does lambda here represent? Anyone?
Total force of transition.
Yeah, so it represents the total force of transition out of the state I, right? But again, we also know, just give me a minute. Yeah, so we also know what is the another thing that lambda I has, right? So if I'm talking about the average holding time in one particular state, what is it? So let me just write it here. Average holding time in I is what? 1 upon lambda I, right? From the exponential. So this is the mean of the exponential guy. So if I know that the average time in A state is 2 days. So basically I know that my 2 is equal to 1 upon lambda A. Then I can easily rearrange this equation and I can get my answer for lambda A, which will be what? 1 upon 2, right? And similarly, for L, I will have 1 upon 10. And for I, I'll have 1 upon 5. And for these guys, it's just going to be 1 upon 1. So 1 itself, right? And now once you have all of these, so you have Pij's and you have lambda i's. Now it's easier for you to figure out this mu ij's, right? But again, remember this formula is valid for all the cases where you're transitioning out of state I. So this formula will never ever give you the diagonal elements of this matrix. It will only give you the other elements except the diagonals. And then to figure out the diagonals, you will have to use the fact that the addition of the rows of a generator matrix is 0. And then you will just write in diagonal the minus of the rest of the guys' additions. Does this make some sense to you guys?
Lambda S will be 1 by 2.
Lambda S should be what? Oh yeah, 1 by 2. Yeah,
1 by
thank you very much. Yeah, makes sense. Thank you very much. Yeah, I have written it here. So it should be 1 by 2. Perfect, right? So let us say, for example, I cannot figure the diagonals, right? So I'm just going to forget about the diagonals. What we'll do is figure out A to L. So PAL is what? 0.1 and times lambda A. So 0.1 times 0.5. That will be your, this guy, 0.1 times 0.5. And now if you have to figure out I, so basically what you'll have to do is multiply each of these rows by respective lambdas. So this everything will get multiplied by a half. So 0.5 square. And this will be 0.4 times 0.5. But again, you forget about the diagonals for now. You cannot specify the diagonals here. So this is everything that you can do. And now if you want to go from L to A, yeah, you can't go. So diagonal, you're gonna leave it blank for now. Let me just put a blank here. And now if we want to go from L to I, this is 0.3 and times 0.1. So this is going to be 0.3 times 0.1. Then this will be 0.7 times 0.1 and this is again going to be just 0. This guy will be 0, 0, something here, and here we have 1 here. So this will be 1 by 5 as it is. And this is going to be 0 again. And here we have 0, 0, 0, 0, 0. We can't say, and this is 1. So this is just 1 upon 2. And here we have 0, 0, 0, 0. Oops, this cannot be 0. This should be 1. Okay. So now I guess it's easier for us to figure out the diagonals, right? So maybe I should just write it here to figure out diagonals. Use So you will basically just add all of these up. So here you'll get minus 1 by 5, minus a half. This is just going to be 0. And this will be something and this will be something. So this is your generator matrix. And let me just write down the answers that you will get here. This will be minus 0.5. So again, if you just have a look, what you are getting everywhere is just minus of the reciprocal of the holding time, right? So basically holding time is 2. So this is what? Minus 1 by 2. This is what? Minus 1 by 10. This is what? Minus 1 by 5, minus 1 by 2, and this is 0 here, right? So basically, I mean, apart from this guy, which is the absorbing state. So this is where you see some difference. But for the rest of the states, you see what's happening. Why? Because again, we also know that lambda I is nothing but minus of mu I. And all of these are mu i's. So if you again multiply this with minus, you should get lambda i's back. And that is satisfied here. So these are again just some small tricks and the way you can kind of check whether your answers are correct or not. So I hope that's clear. And now once you have figured out this generator matrix, then there's nothing much left, right? You'll be given or you'll be asked some probability, and then you just have to figure that out and so on and so forth, I guess. So maybe we can do a sum here. Okay, I think maybe we should just do this. So I guess any doubts in this? Any doubts in what we have discussed up until now? Anyone? Okay, so now if I tell you guys to derive this probability, so let us say I want you guys to give me the probability. Let me just write it in terms of words so that I can know if you guys can say what it means. Yeah, so this is what I want. This is my question. So what in terms of the general notations that we write, Pij, what do you think this particular question is trying to ask me? Going back to the diagram that we had. So again, remember, this is about the claims arriving. And then once the claims get lodged, it can either be L, I, or S. So these are all the different possibilities of how your claims can be lodged. So over here, we haven't yet lodged the claims. So maybe you would want to read the question again. Anyone? What do you think the question is trying to ask? So I would suggest for you all to just keep the summary page open in front of you so that you can see what all formulas do we have and what all stuff we have studied. And then based on the question, you can easily see which one is to be applied where. And I guess it might be a bit trickier for you to see which formula should be applied for what kind of a question. But as in when you practice, I guess that should be much more clearer and quicker. So now, but again, even to see what formula we should use, we should be able to at least write in terms of math the word problem that we are given here. So that is the only thing I'm asking for you to do now. So what do you guys think? What is the question trying to ask me? Am I audible? Hello?
Is it probability of xt is equals to c given that x naught is equals to a?
Oh, wait. Probability that xt is equal to
c given that x naught is equals to a.
Okay. So how many of you agree with what she has just said? So again, was that was Savri, right? So Savri,
Yes.
if you are saying xt is equal to c, what does it mean? It means that the claim has been lodged and basically it has been settled, because only once a claim is settled, it can go to C, right? Otherwise, there's no way it can go to C. And for any claim to go to C, it has to be lodged. But the question is saying that the claim is yet to be lodged. So do you agree with what you just said? Is that what we want to figure out?
Ma'am, will it be probability of xt is equal to a given that x naught is equal to a?
Exactly right, because again, we haven't lodged the claim. So what we are trying to say is that it has just only arrived. We haven't lodged it yet formally. So there's no way it could get complete or P in S or I or L. Sabri, do you understand this?
Yes, ma'am.
Okay. So in the terminologies that we use, again, so just to tell you guys, we'll have to use Kolmogorov's forward or backward differential equations to figure this probability out. So let me so again, just let me know if you think there is any shortcut that you might use here. But the way I can write this particular thing is P, A, T, right? I go from A to A in some T time interval, right? Do you guys agree with this? Okay, now, so tell me, can I write this same probability as PAA bar T? So I want to know what do you guys think? Is this correct or is this correct for this particular question? Which one of these is correct? Come on, I don't want you all to, sit idle. Can you guys hear me? Hello?
Yes, I'm audible.
Okay, so what are you guys thinking? I mean, you can think aloud. Just let me know what are you guys thinking. What do you think is the difference between this and this? Anyone? Isha, can you explain me the difference between this and this?
Between PAAT and PAA bar T, right?
Yes.
So PAAT, will it be something like I'm going from so I don't think it will be possible under this case, but basically I can switch states in between. So I can go from A to L and then back to A. And
Okay.
all of this happens in time t. So basically I think switch to another position, but a bar t means that I'll remain in A itself throughout time t, right?
Okay. Yeah, that is correct. So what do you think? Is this asking you this or is this asking you something about this?
The top one.
The top one. And why do you think it's the top one?
Because there isn't any other condition specified which tells me that I should remain in state A itself.
Right? Exactly. So I guess that is good. But again, I guess as Isha rightly figured out, that in this particular model, there's no way you can go back from L, I, or S to A, right? So PAAT is just going to be equal to PAA bar T, right? Does this make sense to you guys? So generally, the only difference between PAA bar T and PAAT is that PAA bar will only account for A to A cases, right? But let's say if you are looking at PAAT, then what this would have is PAJTs, right? And then mu JA in very small time interval plus PAA and mu AA, and this is nothing but PAA bar T that we have. Why am I writing T's here? Do you guys agree with what I have written over here? But again, all we know is that if we go from A to J, then this mu JA for this particular model is 0. Because you cannot go from L to A, you cannot go from I to A, and you cannot go from S to A. So this is 0 anyways. So this PAAT is just equal to PAA bar T in this particular model. As this is not possible, right? Okay, so now can you tell me, so again, we have studied one particular formula to figure out this occupancy probability, right? I call this as occupancy probability. So what do you guys think should come here? Okay, maybe what we can do is, let us just try to figure this thing from the first principles without using the formulas. So this is another method, or I'll tell you guys one shortcut method by which you can directly write just the answer. You won't even have to figure anything out. But the usual method that you would use, so again, this might not be true for every case, but here it just makes your life a bit easier. So first of all, what you will have to do for any question is to start off with writing your Chapman-Kolmogorov equations. So again, what you will have is PAAT plus H. And again, do not be scared that they have said that, okay, this should happen in time t, but we are adding a H here. Because again, at the end, you take limit when H goes to 0. So that is the final answer that you always decide. So again, even if you have t plus H, it is fine. So we exploit this, and what I can write this as PAAT times PAAH. So again, because here what it's saying is that this claim is yet to be lodged. So again, I would say ideally this is not the correct answer, Isha, right? Because what is saying is the probability that a claim is yet to be lodged. So the claim shouldn't be lodged anytime. So in the time t, there's no way A should go to L and then come back to A. We are only considering the possibility where A. Every time it's just A. You cannot lodge a claim and then come back to A. I mean, that is one case. But again, this PA is, I mean, we just aren't considering PAA here. What we are considering is only this PAA bar, because the claim should never be lodged. And once you exit A, the claim is lodged for sure. So again, this is, but this was, I just explained this for any other cases where you might come back from L or something else. Okay, so for these cases, what we know is that we stay in A forever, right? And this is what we have. So again, I mean, also you assume Markov property. So sometimes in the questions, you will not be given all the assumptions. So you will have to see what assumptions do I need to make to move forward with the analysis that I want to do. So again, I'm assuming Markov property. I'm assuming that this is a valid Markov process. All right. So now what I will do next is I want to figure out this PAAH. So how can I figure this PAAH out? What do I know about the transitions that take place in a very short time interval H? What do I know about them? So do you guys remember something like, Pijh was equal to what? H times mu ij plus O of H. And this was if I equal to J, I guess. No, this was for I not equal to J, right? Do you guys remember this formula? Yes or no?
Yeah.
Okay, thank you, Ishna. Yeah, so we'll use this. So use this to figure out PAL H, PAI H, PAS H, and PACH. Why? Because I know that from A, you can either go to A, it can either be L, or it can either be I, or it can either be S, or it can either be C. And I know this is just 0, right? Because this is not possible. So if I add all of these probabilities, the probabilities that you start off at A and you end up in any state, basically I've taken 5 of these for all the 5 states that we have. This will always add up to 1, right? So if you can figure these 4 out, then this will essentially give you PAH if you subtract these from 1, right? Or else you could just use the other formula where you have I equal to J and this formula I don't remember. This is much more intuitive to me, so I can remember this formula. But again, if you feel comfortable, you can use the other formula as well. But here, if I have PALH, this will be what? This will be H times mu ij. What is mu ij in this particular case? For A to L, what was it? It was, I guess, 0.5 times 0.1. Yeah, it was 0.2. So A to L, right? 0.5 times 0.1, and that is just 0.05. So this will be H times 0.05 plus O of H. Similarly, your PAIH will be 0.5 square H plus O of H. And this guy will be 0.2 H plus O of H. And this is just 0, right? Because this is just not possible. So this is just going to be 0. I mean, but again, ideally, if you're writing equal to, you should write O of H. Because there is a very, very slight chance that this might go to C as well. But that never happens when H is 0. So you have O of H here. I guess. Yeah, so this is O of H that you have here. So now if I were to write my PAA, Therefore, using this, what will be my PAA? If you subtract everything, and again, you don't write this as 4 times O of H, you just write it as 1 O of H. So what you will get here is for PAAH, this is not going to be PAA, this is going to be PAAH. So what you will have here is something like 1 minus blah blah blah, which I'm not going to write again, and I'm just going to write the final answer, which is what? 0.5. Right? So I guess this is just 1 minus. Does this make sense? Okay, so do you guys agree with what I have written on the board over here? So now what you will do is, you will take this PA of H and substitute in here. So if you carry this here, what you will now get is, for PAA, T plus H, this is equal to PAAT. Remember, this is what we want to figure out, times 1 minus 0.5H plus O of H. So this is what you have. And now we'll just have to solve this differential equation. But again, this is kind of easy, right? So what we can do is just write PAA, T plus H here, minus PAAT. And what you will have left here is minus 0.5 times H plus O of H. So I'm going to take in denominator the H here as well, so that the H over here will get cancelled out. But again, I forgot to write that this 0.5 will have PAAT multiplied, right? Plus O of H. And again, now if you take limits, so again, I would say you take limits and stuff, and what you will get here is D of PAAT with respect to T is nothing but minus 0.5 PAAT. So now this is the differential equation that you get. And now you can again solve this particular using the separation variables method. Or maybe I guess, at least for now, I can show how to do that as well. So what if I rearrange that? What I'll have is dPAAT upon PAAT, and I'm planning to take the dt that I had here over here. So what I'll have here is minus 0.5 dt, and I'll just put integration everywhere. So again, I know 1 upon x is so again, can someone tell me what should I write? What should I rewrite this thing as? It shouldn't even take you like a minute to think. What can I rewrite this thing as?
Log of PAT.
And right, this is just log because derivative of log is 1 upon x. So again, this is just log PAAT. So this is what you have. Again, I'm just going to write one particular constant here. Okay, so now once you have this relationship, now you can convert everything in terms of PAA. So your PAAT is just e raised to minus 0.5t plus c. Okay, but we can also figure out this c, right? So to figure out c, what I will do is, again, the very thing that we have here, what we should just do is substitute instead of p 0. What happens if there is nothing? So because we know that PAA0 will be what? 1, right? Because if there is no time elapsed, then you expect yourself to stay at A itself. And that is what you have here. So PAA0 is just going to be 1. Therefore, PAA0 using this formula will have e raised to minus 0 plus C. So this is 1 and this is again 1 plus C. So this gives you that C is just 0, right? And therefore, your PAAT here is nothing but e raised to minus 0.5 t. So this was a very long derivation, right? But this is what is done in your books. They haven't said that this PAAT is just equal to PAA bar in this case. But otherwise, what you could have done is, used this formula directly, right? So PAA bar T would be what? E raised to minus lambda AT, right? And what is my lambda A here? Anyone? My lambda A is just 0.5, right? And that is what we have derived here. So this would, using the formula that we have previously seen, this will just be what? E raised to minus lambda I, which is was just 0.5 T, which is exactly the same as we derived using this Kolmogorov equations and blah, 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 right? Does this make some sense? So again, not every time you will have to succumb to using this derivation and everything. Sometimes you can just use the shortcut, and if you get used to the formulas that we're studying, then you'll see sometimes that you can't do away with heavy calculations. So I would say this is just one of the sums that I wanted to discuss in the class. And now what we can do is, yes, Vanshika?
Depend on marks. Like if the marks are more, we are expected to solve the derivation.
Oh, yes, it does. So every time in this, so again, it depends on the marks as well. And if you are asked to specifically derive this, which is what will generally be the case, then you'll have to derive all of this. But again, generally nowadays they are asking MCQs. So they will, they'll rely on the fact that you won't be solving these equations. But the only thing that is important in this question is, 1, to figure this generator matrix, and 2, to be able to write these equations, I would say. You want to know what you want, and that should guide what you should start with, so that at the end you get something like this, where you can see that I'm looking at the derivative of PAAT. So maybe what you can sometimes do is just figure the stuff that you want to figure out and then write its derivative in using first principles. Then you would know what to start off with. So if you get this, then you will know I want to write PAAT plus H. And then you can go on and write PAAT plus H. So this you can maybe do in the rough work. And then this is what you will write on the fair, and then solve it again to get to this, and then so on and so forth. So I would say that was it. And again, I think, yeah, so this is just one particular example, and there are many other examples as well. So you can, so I guess we'll try to solve one more question and we'll see how does that happen. But before we do that, there's something else that I want to cover, and that is the maximum likelihood estimator of the parameters that we have. So again, in this case, the parameters that we have will be the transition rates, right? From one particular state to the another state. And these transition rates are the parameters that we want to write the likelihood for. And then we will try to maximize that likelihood. And then if we maximize it, and we'll basically get the answers. But again, I think I am not going to write all of it. So let me just open the book. So again, this MLE is going to be almost similar to what we did in the previous chapter for the mu, right? We had only 2 states, alive and dead. And we figured out the MLE, we figured out the mean, we figured out its variance using the CRLB, which is Kramer-Rao lower bound. But let me just open this once. We're looking at what? MLE. Can you guys see this? So again, the only difference that you have here and the model that we studied was they never put P anywhere, right? Because we always assume that these transition rates are constant, and that is what we are going to assume now as well. And in the next chapter, we will have time in homogeneous case, which we'll see, I guess. I better not say anything about that now. Okay, so now if I want to figure out what is this question. Yeah, so now these are some statements that are being given to us and some stuff that we will have to use to figure out this particular likelihood. But again, I guess maybe I should just explain how do we even get that likelihood, because they haven't quite actually explained that here. They have just said that this is equivalent to blah, blah, blah. Okay, so we have healthy, sick, dead. This is something, this is sigma, rho, mu, and mu, right? And what they have given us is the waiting time in healthy state, which is VI for one particular life I. WI is the waiting time for the life in the sick state. And then they have given us the number of transitions that we have for each of the transitions. So from healthy to sick, we have S number of transitions for one particular life. So we know that if there is only one life, it can be healthy in one time, then become sick, then again become healthy, and then stay healthy, and then eventually die. So for one life, we could have a number for SI, RI, DI, and UI. But again, these numbers will always not be independent, as we might think, because again, so let's say if I say, we know for sure, right, that a life after 200 years is going to be dead for sure. So what all can we have? Let's say if a life, okay, maybe let me just say first that, okay, so number of transitions from healthy to sick is S. I'm writing this in red. From sick to healthy is R. From healthy to dead is D. And from sick to dead is U. Right? Okay, so this is what we have here. But now if let's say I ask you guys some question, if someone has already made this transition, right? If DI is equal to 1, we know for sure that DI can never take a value more than 1, right? Because the number of transitions from healthy to dead for one particular life can be only 1. And once it is in dead state, this is absorbing. You can never go anywhere else. So DI can either be 1 or 0. And similarly will be the case for UI. This can also be only 1 or 0, depending on whether the person dies when he's sick or healthy, right? And again, we also know for sure that if we are talking about the same person, that same person can either die when he was healthy or die when he was sick. He cannot simultaneously be healthy and dead and be sick and dead, right? Either he should be at H or he should be at S before that guy dies. Before that guy dies. Yeah. So now we also know for sure that this DI and UI cannot simultaneously both be 0 or 1. So if I'm saying that a particular person is dead for sure, let's say, okay, then what do we know about DI and UI? We know for sure that if my DI is 1, then UI is definitely 0. And if my UI is 1, then my DI is definitely 0. Does this make sense to you guys? Hello, can you guys hear me?
Yes, ma'am.
Thank you. Okay, so this is one observation that we have, but there's one more observation. So if I care about the number of transitions that are done from healthy to sick, which is S, and the number of transitions that are from sick to healthy, which is denoted by R here, right? Is there any relationship between S and R? So again, I'm saying that this person dies at the end. So we know for sure that this person, if he's dying, then he could either be in healthy state or he could be in sick state, right? So let us, for now, let me assume that today the person is at healthy state. Okay, and I know that after some time t, this person becomes dead, right? So I want to figure out how many transitions this particular guy must have made of from healthy to sick and from sick to healthy. So if I basically say that this guy when he died was in the healthy state previously, right? If I say that this guy when he died was in healthy state, I know for every time I go from H to S, I should come back from S to H as well, because I cannot stay in S and be dead. I die when I was in healthy state. So every time I go from H to S, I should come back to H as well. So my S will just be equal to R here. But again, if I say that I was at sick state when I died, then you know for sure that the number of transitions you make from healthy to sick is one more than the number of transitions you make from sick to healthy, for sure. So your S will be R plus 1. And again, these are true for one particular life. So again, this is basically also true if you put 0, either SI0 or RI0 as well. But again, I would just say that, these are just some observations that we have made to say that the number of transitions that we have from one particular state to another state are not independent. So these are not independent. But again, the very basis of MLE is that we assume that when we are looking at a very, very large interval of time and so many lives simultaneously, not only one particular life, then this becomes independent. So the number of people you will have in particular state at a point in time will be independent. So again, if you have many number of people that you're looking at, so generally that is the case. But again, whenever it will come to our calculation, we'll only be doing it for one person, and we will make an assumption that asymptotically these random variables are independent of each other. So that is something that you should keep in mind even before we try to derive its likelihood, I would say. Okay, so now again we'll try to see how do we determine these likelihood. So let me just erase all of these. Oh, I should have kept the drawing, but I guess you guys know by now at least. Okay, so again, whenever I want to figure out the MLE of these particular rates, what all possible transitions I can have. So again, I'm just going to, this is mu, sigma, rho, right? So we have all of this, and we know that, so what we will do now, so again, we'll have to take these into consideration as well, right? When we try to map out all the possible cases, all the possible probabilities that we can ever encounter. Okay, so let me just assume for now that we are going to start off in a healthy state. So let's say if I start off in a healthy state, the probability that I'll be in a healthy state once again is what? So again, I'm not going to count the fact that it could go to S and then come back. So I'm just looking at HH bar. So it will just be E raised to minus the total force of transition out of state H, which is mu and sigma. So minus of mu plus sigma and times P. So here, what does RT denote? It denotes the waiting time in H, right? And we know for sure that waiting time for one particular life is VI. So again, let me just say that we are writing all of these for only one particular life for now. So for H2S, I will have e raised to minus mu plus sigma Vi. So this is what will happen in T, and then in H, I want to make a jump, and that will happen with what? Sigma. So here for D, you will have e raised to minus sigma plus mu Vi, and this will be mu, right? So this is what you will have for the healthy state. And again, you can also start in sick state, and from sick to healthy, from sick to sick, and then you can be dead as well. Okay, so first of all, I can write this. This is very easy. Minus rho plus nu, and here I have Wi, right? And for H, I'll have e raised to minus rho plus nu Wi, and this is rho. So again, we are writing this only for one particular life, and that is why we only have rho here, nothing, because it's just one. And here I'll have e raised to minus rho plus nu and Wi, and this will be nu. Does this make sense to you guys? So this we have analyzed for all the possible transitions that we can ever have. But now what I will be doing is, so for any one particular life, this is all that you can observe in a single time. So what I am doing when I say that, so again, there is only one possibility, right? That my life will either start at healthy state or it will either start at sick state. There's no way it can start at both of these. So, but again, what I have kind of taken into consideration is that if you go from H to H, then again you can go from H to H, S or D, right? So if you go from H to S with this, you can again go from S to so and so. And why I haven't mapped this out for D? Because after D, you can never go to H or you can never go to S. So there's nothing that's going to happen after this. So if I essentially multiply all of these probabilities, I should get my likelihood for that particular person, right? And if I do this for all the individuals that I have, then what will I have? So let me just try to maybe write here. Let's say if I try to write the likelihood. Okay, let me just try to write this. You will have something as, so you will have these probabilities. Let me just write it for one particular person for now. So I have e raised to minus mu plus sigma Vi. And again, this gets multiplied. So each of these will get multiplied, right? Each of these will be multiplied to each other. And what you will essentially have is this thing times, okay, I'm not going to write all of this stuff.
Ma'am,
Yes, Isha?
for the healthy to sick part,
Yes.
so is it something like first we are assuming that the person will go from healthy to healthy and then to sick with sigma?
Yes.
And then what is it for D? I didn't H to D.
The same thing, right? It's mu because from H to D, the jump will be at the rate of mu. So the probability that you will go from H to D in some time T will be this.
But H to D, so H to D it can go via like H to S and then S to D also, right?
Okay, I'm not taking that into consideration here. I'm only taking, the one transition that you make from each particular state. This is only one transition that I'm taking care of.
Okay.
So this is direct jumps from H to H, from H to S, and from H to D, no via. So if you want to go from H to D via S, you will have H to S and then S to D. So you'll essentially multiply. So you will essentially multiply these probabilities and you will get this answer. Okay, so now let me just try to figure out a way so that I can write this likelihood. So okay, so maybe what I can do is I can just summarize this for every time a particular life is in healthy state, every time a particular life is in sick state, and for every time a particular life is in dead state. And what are the chances that this will happen? So for healthy, you will have this and this thing. So this and this will be multiplied here. For sick, you will have this and this will be multiplied here. And for dead, you will have this and this multiplied here. So if you kind of have a look in general, what you will get at the end, again, I'm not going to write it down. So what you will get at the end is these mu, sigmas, rhos and nu for each of these people, right? So what happens now is we have said that the number of transitions from healthy to dead are D, I. So this is for one particular person. And now if I add up all of these DIs, let's say D1 plus D2, I will get my capital D. And so I have my capital V and all these capital letters without the subscripts if I add it for all the other people. So what you will at the end have is this thing, this mu will be raised to the number of people you observe, the number of times you observe people going from healthy to dead. So this could again, this can never be greater than the number of people that you have because a life can never twice go from healthy to dead. It can only go once. So here you see you have mu raised to D and mu raised to whatever their respective numbers you have here. And then this you will, this you can just take it as common outside. But again, here you might wonder that why do we only have one of these? But we are multiplying this so many times, right? So what will happen is if you multiply this, because you have e raised to the similar things, this will get add up. So summation vi, summation wi, and summation vi will give you v, and summation wi will give you this particular w that you have here for all the lives cumulative. So that is how you kind of derive this likelihood function. But again, not necessarily you have to know how to write this likelihood function, but I would say, so because I think we have already derived the result, which makes sense. At least we saw that in the previous case where we did it for our mu case, the mortality rate, right? But again, here we'll see that it might be a bit different or it may not be a bit different and just the same. So that is yet to be revealed to us. But we have this as likelihood. Okay, and now once we have this likelihood, we know what to do. So here what they have done is they have just segregated this. So they have taken this e raised to minus mu v and mu raised to d along with it. So e raised to minus v is common, but the other rate that you have here is mu. So they've taken the mu by here, and for sigma, they've taken this sigma here. For mu and rho, again, the same thing. So that you get this separate stuff for each of the parameters that you have, because at the end, what you'll have to do is differentiate this log likelihood with respective parameters. So to make that easier, they have just combined all these stuff that has one particular parameters in one bracket and then multiplied it with log. So if we have, sorry, you cannot multiply it with log. You apply a log here and all of these e's will just come down as it is, and basically you get this, and for mu raised to d, you will have d times log of mu. For this guy, you will have s times log of sigma, and so on and so forth. And now if you differentiate this thing with respect to mu, let's say, if I do d of log L by d of mu, what do I get? I get this thing, which is minus v. This is not new. So yeah, you should also be aware of this, okay, whenever you're writing. This is new and this is v. This is waiting time and this is the transition rate. So this is v here, and here I have plus b upon u, and I make this equal to 0. So what do I get here? I get that my mu is equal to v is just d upon v, right? So D is what? D is the number of transitions that you make from healthy to dead. And V is the waiting time in healthy state. And this is the mortality rate, healthy to dead. So these kind of make sense. So similarly, if you do this for each of the other variables, each of the other parameters, you will get these respectively, and these will be the answers that you will have. And again, now because we have so many different parameters, basically 4 parameters that we are trying to check. If you want to go and check the second derivatives of this, you will have to do this particular matrix. And this is actually known as Hessian matrix. And this will be, so basically the reason, so if you read here, they say that, this Hessian matrix should be negative definite. And it's negative definite when the eigenvalues of these metrics are all negative. But again, we don't have this thing in our syllabus. But just to tell you guys, when we say that the eigenvalues are negative, it just means that there will be, the process won't just go on and on forever. It will settle down and it will become stable. So there will be stable solutions which will exist. And that is why you need these Hessian matrices eigenvalues to be all negative. And that happens in this particular case. So yes, these are the estimates that you get for each of these parameters. And again, yeah, they have said that checking the Hessian matrix is beyond this syllabus. And there is a whole different matrix theory that you can study about eigenvalues, eigenvectors, but again, eigenvalues and eigenvectors form crux of very so many concepts in financial applications, I would say. So I guess it's kind of nice if you want to delve deeper into it. You should definitely look up. I can maybe put up, I don't know if you guys know how to, what exactly is a determinant of a matrix, right? When we say that I have figured out a determinant for a matrix, what does it mean? You can't basically visualize determinant, right? But again, just to give you guys one idea, if you're calculating the determinant of a 3 by 3 matrix, it is the volume of a cube which will be formed if you plot these elements as the coordinates. So I think I will just put up the link of Grant explaining this stuff. But yeah, for us, we know that these are the estimators that we have. So again, these are the sample values, and these are the estimators. So again, this is estimates, and this is estimator because we have capital U, capital B, and everything. Here we have small. So I guess this is what I wanted you guys to know about the MLE of these particular parameters. So maybe we can have a look at some example.
Ma'am, can I leave now?
Can you? Oh yeah, sure, Isha. No worries.
Yeah.
No worries.
Thank you.
Okay. So now what I want to do is, so they have just generalized it. And now if you just have a look at this example, this is pretty easy. So not much needs to be done for the MLE of these parameters. So here what they are saying is that during a large study into rate of sicknesses, you know that these many healthy lives fail sick and these many sick lives recovered. So from healthy to sick this much, from healthy to sick this, and from sick to healthy this. Recovered means healthy again. And you have 70 lives dying and 120 sick lives being dead. And then for the whole group, the periods of health and sickness totaled 41200 and so on. So they have basically just summarized the information here. So this TH represents the waiting time in healthy state, waiting time in sick state, and healthy to sick number of transitions, so and so forth. So every time you want to figure out, let's say sigma hat, this will be H2S upon H, NHS upon TH, and so on and so forth for the rest of these parameters as well. So I guess that is all. But again, if you remember, we figured out the distribution of mu, the estimator of mu, right, in the previous chapter. So I'm not going to do all of those derivations again. And so again, here they are assuming that these are asymptotically independent, which is, yes, the same argument that we made in the previous chapter. And in the previous chapter, we derived this, right? we derived that expectation of mu tilde is just mu, and the variance of mu tilde is mu upon the total waiting time that is expected in the particular state that it refers for. So if we know that mu is from healthy to dead, so this expectation of v will be for healthy state. So I guess this is clear. And again, they say that these components are uncorrelated, and so yes, they are asymptotically they are uncorrelated as well as independent. And if we aren't talking about asymptotically, then they will be uncorrelated but not independent. And we know that can happen. So I guess the next thing that you will have is these distributions for each of the variables each of the parameters that we have studied. So this is the marginal asymptotic distribution of V, sigma, and rho's estimators respectively. So again, these are estimators. Why? Because we have tilde 1 and 2 capitals. So remember, you'll write capital here, never small one. And these are just the properties that each MLE satisfies. Okay, yeah, they have just said how you derived these. So yeah, the very fact that the expectation of rho tilde is rho says that it is asymptotically unbiased. And yeah, so okay, so now about calculating this expectation of W, expectation of V, and so on. This we will study in depth in further chapter. But again, just to tell you guys now, in the previous chapter, what we studied was what happens if you go from alive to dead, right? Let us say if you're looking at one particular year. So we used to say that, if I'm looking at lives that live from the age of 59 to 60, and I have some data, and if a particular life dies in between, then what do you assume? Do you assume their age nearest birthday? Do you assume their age last birthday? Or what kind of age do you assume? So in the previous chapter, we didn't assume any particular age. We just assumed that every time a person was dead, they died exactly in the middle of the year. So the mortality rate that we derived was for mu x plus half, ideally. But again, we'll study all of that. We'll study all of that and the conversions of these in depth in upcoming chapters. So I guess this was it about the theory. But again, I think we should at least try to solve one question which I feel is particularly nice about maximum likelihood. I guess. Yeah, let me just go to that part. Yeah, so guys, for this chapter specifically, these summaries will be of much help, because you need to know what does these MI, MJs represent. So you'll get that. And I guess you can make a flashcard or something if you want. Okay, yeah, this is what I want to do now. Okay, so I want you all to read this particular question and we'll try to solve this now, and that will be the end of the class. So the quicker you guys do, the quicker you can go and relax. So Savri, can you read the question? Can you read this first paragraph for us?
Yes, ma'am. The following multi-state model has been suggested as a representation of death and retirement between the ages of 59 and 16. There are no other decrements, and the forces of decrements mu and are constant. Let denote the probability that a life is in state J at age x plus t, given that it was in the state I at age x.
Okay, so now the very first question asks us, what are the assumptions underlying the above model? So remember all the assumptions that we have to make to derive the probabilities, right? Because that is what will be doing. So can you guys tell me the assumptions? I guess we do make 3 assumptions and we do have 3 people. So each one of you can state one assumption. The one who speaks the first gets to say the easiest assumption. So go on. What kind of assumptions do you think we are making here? So maybe to state this particular statement in other words, what kind of assumptions you will have to make to this particular model for this to classify as a Markov process?
And the probability should only depend on the current state.
Exactly right. So the very first assumption should be that the Markov property should be satisfied. Very good, Mihir. What about the other? What other assumptions do we make? So remember, we also assume that more than 2 transitions or even 2 transitions are not possible in a very short span of time, which we classify as h, which we denote as small h. So there can be only at max 1 transition. And again, I mean, so we don't say that it's never going to happen, but we say that the chance of more than 2 or 2 transitions happening is small o of h. Right? So that is second assumption that we make. And again, the third assumption is sometimes that if I'm looking at a very, very small interval of time, and then my transition rate is constant. So yes, and I guess that even they have given some mu and nu. And if I guess I were to just write it, then these will be the 3 assumptions that we are making in this particular model. Okay, but apart from that, I guess if we look at the B part of the question now, so A part is done. If you look at the B part, what do you guys think is happening here? What are we trying to figure out here? Okay, so I guess 0, 0 means, what do you think 0, 0 means here? Anyone? So we have TPX 0, 0.
It is AA, right? That it is staying at active state.
Is that A? Okay, sorry, I saw it as 0. Oh, all right. Yeah, I guess it now it makes sense. I was wondering what is 0, 0. All right, thank you very much. Okay, so it's okay. So basically, oh, so they have written states upper and time age niche. Oh, okay, yeah. Sorry. Yeah, state I and state J is represent in the superscript. All right. So what we have here is AA, And yeah, so basically this makes sense, right? This is kind of the occupancy probability again, because you cannot be active dead and again be active. You cannot be active retired and again be active. I mean, ideally not in this scenario, but in general you can come back to A. But here we are assuming it does not. And I'm not going to show this because you'll be, so I would actually suggest for you guys to try this on your own and try to show that this is indeed equal to this. This will be something similar to what I just showed you in the lecture. Okay, but this is what I chose this particular question for. Okay, so now what we have to do is we have to write the likelihood. So they've said is that V is the time spent in the active state. Then D is the number of deaths and R is the number of retirements. And now they are like shows the likelihood for mu and nu given these observations. So what do you guys think the likelihood will be? So go back to what we studied and try to figure out how can I write the likelihood function for this particular model. So basically you'll have to see what all things can happen. So remember what we saw first is the waiting time. So maybe let me just go back and say this thing. Oh, I never wrote the likelihood here. All right. So remember in the healthy sick dead model, when we wrote the likelihood function, the very first term that we had was about the waiting time, the total waiting time, right? It wasn't the waiting time for only one life. So we had we had like a small v, not vi in the superscript in the power. So what you will do first is multiply the waiting times of all the states where you can wait and then hop on to some other state, right? And then you will multiply the transition rates raised to the number of times you make that particular transition. So here what you are going to have is, so you can remain in this particular active state and the chance of that happening will be what? Anyone? What is the chance of this happening? It should ideally just be e raised to minus lambda it, right? So, I mean, capital A, just change that. Yeah, so this is what we're looking at. This will just be e raised to minus mu plus nu. And waiting time is what? V. So again, you have V here. So this is what you will have. And again, the kind of transitions you can make. So if you were to write the likelihood, you will write this. I can just show it to you guys. So this will be the first term, and then you can make transition mu, which is go from active to being dead, and the number of deaths you have is D, and the number of retirements is R, which will be raised to the transition rate from active to retired. And that is how you will get your likelihood here. Again, they have given a full derivation of this likelihood, and I would suggest for you all to have a look over there and see how they have done that. It is kind of similar to what I was trying to explain to you previously. But yeah, now they are asking us to give a formula without proof for the maximum likelihood estimate of the parameter nu. So what do you guys think this will be? Anyone? What will be the estimate of nu? Oh, they haven't asked about the estimate. Again, this is, if I put a hat, it's an estimate. And if I am asked about the estimator, then I know it should be tilde. So again, if I'm being asked about the estimator, I'll have to write these in capital terms, I suppose. Okay, but what do you think new hat should be? What do we generally have? So we just saw this, right? Do you guys remember what we derived? So what is new hat? New hat is the transition rate of going from alive to retired, right? So what will this be equal to? Come on, I don't think it should take you this much of time. We don't have to derive it. We just have to write what it is. And what does your intuition say? What is the rate at which people are getting retired from being alive? How will you determine that rate if you know the number of people who retire and if you know the time that people generally spend in total in the active state?
Is it R by V?
Yeah, it is R by V. So it will be R by V, right? Because the number of people who retire and the time that you spent being in the active state. So this proportion will denote the rate at which people are retiring. Simple, right? So I guess once we have this, we also previously derived that this will follow normal distribution with expectation mu itself. And what was the variance that we discussed? It was mu upon the expectation of the waiting time. So I guess the waiting time is V here. So this is what you will have for the asymptotic expected value and for the, okay, so they're asking standard error. So this is the variance. And for standard error, you would have the square root of this particular thing here. So you will just have square root of, I guess, mu upon expectation of V. But again, I think, sometimes you can also replace this expectation of V as just V. It's fine if you do either of these. But ideally, I should say for this case, again, try to remember where do we get this variance from. We get this variance from the Kramer-Rao lower bound, and that will give you V, not expectation of V. This was just something that we studied. But again, this will become much more clearer. The difference will become much more clearer because we say this is expectation of V because sometimes it's really not possible to calculate the actual waiting time. So you figure an approximate waiting time, and that will be expectation of V. But yeah, I guess you guys get the gist. So once we have this, we've cleared the D part. Okay, now there is one more question here. So Mihir, can you read this question for us?
Yes, ma'am. Suppose that you learn that the retirements can only take place on a birthday, so that R is the number of retirements at age 60. In addition to V, D, and R, you also observe M, which is the number of lives attaining exact age 60, where M is less than equal to N. Suppose that any life attaining exact age 60 will retire with the probability K, where K lies between 0 and 1. State the likelihood for mu and k given that v, d, r, and n.
Okay, so what do you guys think is happening here? I just want you guys to explain me what the question is trying to tell. What change has been made? Come on, I'm not even asking you for the answer. I'm just asking what do you understand of this question?
In the
Anyone?
previous question, it was possible to retire at any age between 59 to 60. Now it is possible to retire only after reaching age 60.
Right. So not any person can retire. We are given a condition that only at the exact age of 60, so only on the day of birth, you can move and take retirement, or else you will not take the retirement. And again, the chance that you will take a retirement once you have attained the age of 60 is K. So it is not for sure that you will be declared retired once you reach the age of 60. No. There is still a chance that you might be in active state, you might continue to be employed and not retire. But the chance that you will retire is K, which lies as probability should be between 0 and 1. Okay, so previously the likelihood that we had was this, right? In the normal case, the likelihood was this. Why is this not working? Yeah, so the likelihood was this. But now we know once we have made some changes, this likelihood is also going to change. But what you have to see is what part of likelihood is getting affected. So we can clearly see here that I can rewrite this likelihood as e raised to minus mu v times mu raised to d times e raised to minus mu v mu raised to r. And we know when I make this particular change, I'm affecting this part of the likelihood. So one thing I'm sure is that for my likelihood, for my new likelihood, this part will remain as it is. So I have minus mu v mu raised to d as it is. But this part is no longer true because r does not anymore denote the, okay, no, r still denotes the number of people who retire. But again, that again depends on how many people attain the exact age of 60. So you can't necessarily say that R is going to give you the all information that you require. So there will be some role played by K and M as well. So what do you guys think is happening? Maybe I guess I should just try to explain this because this is fairly new concept. So what is happening here is again, now there is again a likelihood involved because there's a probability in the probability, right? So there is some probability that a person will reach the age of 60. And then there is some probability that that person who has reached 60 will in fact retire. So we can say that this is like a binomial something where a chance where a life could either retire or a life will not retire, right? So the chance of this happening will be what? So with K probability, these lives retire, and the number of people who retire is denoted by R. And if I want to figure out 1 minus K will be the probability that a particular life does not retire. And if I keep on multiplying this for all the lives, what I will get is M minus R, because M is the total number of people who were likely to retire, but only R out of those people retired. So remaining M minus R are the people who have 1 minus K as the probability. Does this make some sense? But again, now as we know, there are so many different people involved. So any of these employee could get retired. And that is why to take into all the considerations that you can have, all the possible combinations that you can have, you will multiply this with MCR. And if you multiply this with this is the likelihood that you will get now. So this will be your new likelihood for this particular change that you have made in the question. So I guess, again, any doubt in this derivation of the likelihood? So I would again say that, see, not every question will be as straightforward. So sometimes there will be like, high order thinking skill type question where you will have to go beyond what's being taught to you and try to see what all is possible. And to be able to solve such kind of questions, I guess you'll have to practice a lot. So if you practice the end of chapter questions, well and good, but you should also try to practice the booklet that I will upload. Not today, I'll upload it in, I guess, 2 days, because that booklet has the next chapter as well. So you guys might get confused. So yeah, this is the likelihood that you will have. So that was for the A part. But now if in the B part, what they're asking us is, again, they aren't asking us to derive it. So that's good. So they're asking us to write the maximum likelihood estimate. So remember, this is an estimate. We'll write in small letters. So estimate of the parameter K. What do you guys think K denotes here? What do you think? So tell me in words, what does K mean? Vanshita, are you there? Yeah. So can you tell me what does K mean here? What is K? In words. I'm not asking you the estimate of K. I'm just asking you what does K mean in words here?
That sorry for the noise.
Yeah, it's all right.
That if a life reaches age 60,
Yeah.
the probability it will retire.
Right. So if I want to figure out my maximum likelihood estimate for parameter K, what will that be? It will be what? The number of people who retire out of the total number of people who were supposed to retire, right? Or who could retire, who had a chance to be retired, right? So this is what you will have as your maximum likelihood estimate of the K parameter. So I guess this is all from my side for today, and I will see you guys tomorrow. So I might take lectures throughout the week. So I guess you guys should read and study whatever we do in the class after the class is over, before the next